Hi everyone, I'm Mingliang Chen from the University of Maryland. I will present a work towards threshold invariant fair classification co-authored with Professor Ming. Machine learning systems have been deployed in our daily life to assist us in automatic decision making. However, some researchers have found that machine learning has bias just like humans when making decisions. For example, the COMPASS software stands for Correctional Offender Management Profiling for Alternative Sanctions, which helps judges make parole decisions in the U.S. courts, usually assigns a higher risk score to African American defendant than to a Caucasian with a similar profile. This may lead to bias on the judge's final decisions. To tackle the problem of machine bias, prior art mainly has three directions. The first group of algorithms map the data to a fair representation in a latent space before the classification. The second group of algorithms impose the fairness definition during the model training. The third group of algorithms calibrate on the decision scores from the classifiers to meet the fairness definition. The classification parity is a widely used family of fairness definition in prior art. One notion in this family, demographic parity, DP, enforces equal selection rates across all the groups of protected attributes. The protected attributes refer to the features among which the classifier is required to have fair predictions, such as race and gender. Another notion is equalized odds, EO, which enforces equal prediction accuracy across all the groups of protected attributes. That is, the true positive rates and false positive rates are equal across the different groups. However, there are limitations in the classification parity. In the machine learning model, the classifier G maps the input feature X into a risk score. Then a binary prediction label is obtained via thresholding. The bottom right figure shows an example of the risk score distributions of two groups. In DP case, the highlighted regions are equal to guarantee the equal selection rates. However, such parity still shows differential performance across the two groups in terms of the risk distributions. Actually, if we change the threshold a bit, the parity will no longer hold true anymore. So we need a stronger restrictions on the classification parity by equalizing risk distribution. We propose two approaches to fulfill the equalization of risk distribution. In approach 1, we use histogram to represent the distribution. We first count the samples in the histogram bins. We use the Gaussian kernel to make the counting operation differentiable. Then, we use the symmetric combination of KL divergence to measure the distance of the risk distributions. In approach 2, we assume the prediction scores obey Gaussian distribution. To characterize the score distributions, we use maximum likelihood estimation, MLE, to estimate the means and the variances of the prediction scores. Similarly, we use the symmetric combination of KL divergence to measure the distance of the risk distributions. When designing the classifier, we incorporate the fairness constraints by adding a regularizer in the training objective. For binary protected attribute, in DP case, EF is the distance of the risk distributions of two groups. And in EO case, EF is the summation of the distance of the risk distributions in positive and negative ground truth labels. We test the effectiveness of the regularizer in three kinds of widely used classifiers: logistic regression, linear SVM, and kernel SVM. We use ProPublica COMPASS dataset where we predict whether the defendant would commit a crime again given his or her individual information. The protected attribute is the race here, meaning African American or Caucasian. we measure the fairness level of the classification. In DP case, by computing the discrepancy of the selection rates, and in EO case, by computing the discrepancy of the true positive rates and false positive rates. We visualize the risk distributions in logistic regression under 3 levels of the constraints. No constraints, meaning the baseline, moderate constraints, and strong constraints. From the figure, we can see that the risk distributions are distinct between the African American and Caucasian. As we increase the regularization parameter, the risk distributions become closer and closer. This suggests that the discrepancy of the prediction performance shrinks on the 2 race groups, and the bias is alleviated, compared with the unconstrained classifier. Here we present the trade-off between accuracy and fairness in 3 kinds of classifiers. Filled triangles indicate the unconstrained classifiers. From the figure, we can see that our proposed methods are effective at alleviating differential prediction performances across the groups at the cost of moderate reduction of prediction accuracy. Delta DP and delta EO reduce from around 0.2, which the baseline shows, to less than 0.05 with the help of the fairness regularization. And in the meantime, the resulting accuracy dropped by approximately 10%. Here we show the parity variation versus classified thresholds. The baseline refers to the unconstrained classifier. The ZFA method refers to prior art with classification parity constraints. From the figure, we can see that the curves from our proposed classifiers are much flatter. This means in our proposed classifiers, slightly modifying the threshold doesn't affect the parity to a large extent compared with the baseline and the prior art. This also suggests that our proposed constraints are effective in reducing the classifier sensitivity to the threshold in terms of the classification parity. To recap, in this talk, we show that the classification parity still have differential performance across all the protected attributes. We propose stronger restrictions on the fair classification via equalizing the risk distribution. The experimental results show that the proposed algorithm effectively alleviates the prior issue that the fair classification is dependent on the classifier's thresholds. Thank you for your attention.